Hello everyone, today I am going to discuss the new topic, that is compaction, and this topic comes under the unit 4. So basically in unit 4 there are two sections, compaction and consolidation. So in this topic I am going to discuss all these contents. So I will start from the introduction. So you know that in many engineering structure, soil is used as a construction material. In the construction of engineering structure such as a highway, embankments or earth dam, for example, loose fields are also required to compact it to increase the soil density and improve their strength characteristics. So from the improvement of soil characteristics and soil properties, so compaction is a very common and very simple method. So we can define the compaction. The densification of a soil by the application of mechanical energy is known as the compaction. On the other hand, we can say that pressing the soil particles close to each other by applying the mechanical energy, we can call it compaction. So during the compaction, air is expelled out from the void space in the soil mass and therefore the mass density is increased. So by increasing the mass density, shear strength of soil is also increased, bearing capacity of soil is also increased. They are all related. So in the geodetic second part, we can discuss all this relation. So in this figure, you can see that I have shown the two separate section, that compaction and the consolidation. So from the first part, A and B is showing before compaction and after compaction. So in the case of first figure, A part, there is a three-phase system. There is a water, air and solid particles. After the compaction, you can see that only the reduction occur in the volume of air. Means total volume of soil is reduced due to the reduction in the volume, only volume of air. Means volume of water is not changed. Volume of water is constant and volume of solid is constant. I know we already discussed the volume of solid particles. We take as a constant, it will not change by any operation. So the total volume of soil is decreased by the decrease in volume of air. But in the case of consolidation, the soil is fully saturated and there is shown a two-phase system. There is a water and solid particles. And after consolidation, the volume of soil is reduced due to only by the reduction in volume of water. So in this case also, volume of solid will not change. So total volume of soil is reduced by the reduction in volume of water. So what we can say that the consolidation causes the reduction in the volume of saturated soil due to the squeezing out of the water from the soil. Where in the case of compaction, the volume of partially saturated soil decrease because of the expulsion of air from the voids without changing the water content. Means in the case of water content, in the case of compaction, water content is not changed. Or we can say that consolidation is the gradual process of reduction of volume under the sustained static loading caused by the weight of building and any other structure. Whereas in the case of compaction, the rapid process of reduction of volume by means such as a rolling, tamping and vibration. And compaction, we can say the compaction is also an artificial process. So these are the two difference between the compaction and consolidation I have shown. So compaction is the instantaneous process. And consolidation, time dependent force, it's take a lot of time. Compaction already occur in the partially saturated soil sample, means unsaturated, and consolidation occur in saturated soil. During the compaction, air expelled out, and during the consolidation, water expelled out. And this is the static specified compaction techniques. We do a lot of the laboratory tests performed to do the compaction to improve the soil characteristics. In the case of consolidation, it occurs due to the static loading. but it can be due to the weight of a structure or weight of building. So here I have discussed the one laboratory test. So R.R. Proctor in 1933 has performed one test that is called the Standard Proctor test. So they have used a specification. So the Proctor used a standard mold of 4-inch internal diameter and an effective height 4.6 inch with a capacity of 944 centimeter cube. So the soil was compacted in the mold in 3 equal layers, or for each layers was given 25 blows of 2.495 kg rammer falling through a height of 304.8 mm. So all the description I have shown in the table. So for a standard Proctor test, all the data are given. So they have to perform the test, and after the test they have calculated the water content and the dry density, and they perform the different test, means a number of tests, and for each dry density they calculated the water content, and for each water content they calculated the dry density, and they have plotted in the graph where the dry density was in vertical axis and water content was in horizontal axis, and that graph is called a compaction curve. So after some modification, that test was called a modified Proctor test, in which test you can see that there is a weight of hammer change, height of falling change, means we are giving high energy. So here the compacting effort is increased in this case of modified Proctor test. So light compactor test and heavy compaction test we use in India. So there is also a IS code. So for the light compaction test, IS code is 2720 part 7 1974, and IS code for the heavy compaction test IS 2720 part 8 1983. So we can go through all this IS code, so you can get all the details about this test. The question number 1, compaction of an embankment is carried out in a 500 thick layer. The rammer used for the compaction has a foot area of 0.05 meter square, and the energy imparted in the every drop of hammer is 400 Newton meter. Assuming 50% more energy in each passes over the compacted area due to the overlap, and the number of passes required to develop compacted energy equivalent to the Indian standard light compaction for each layer would be. First, understand the question. It's saying there is a thick layer 500 mm and the embankment. So that they are relating from the Indian standard light compaction test. So for the Indian standard, Indian standard test, we have this data: volume of a mold is 1000 cc, weight, height of fall, n, or number of layer 3. So we can calculate the energy imparted. So we can calculate the energy imparted simply. We can multiply the weight of hammer into the height of fall. But the height of falling happened 25 times and in 3 layers. So we are multiplying all this data, we can get the energy imparted. So we got the 593.01 Newton meter. So this energy 593.01 Newton meter required to compact the 1000 cc, right? Let's calculate the case of embankment. So the volume of soil covered by the rammer. So what will be the volume of cover? So the area will what? Area of foot and into the height of clay thickness, thickness of clay layer. Okay, so we can calculate the A into H. So we get the 25,000 cc. Means we have multiplication. We have done the multiplication of area of foot of hammer into a rammer into the height of thickness of soil layer. Okay, so we got the 25,000 cc. So energy imparted in that case. So in each layer you can get the 400 Newton, but 50% more energy in each passes over the compacted area due to the overlap. So we can calculate the total energy imparted in each pass, 1 plus 50% into 400. We got the 600 Newton meter. Because the 50% is energy due to overlap. So we have to calculate that. So what is the meaning of this 600 Newton meter energy required to compact 25,000 cc? So we can compare the both this embankment compaction to the compaction due to the Indian standard. So we can calculate. So suppose n number of passes required to develop the equivalent energy to Indian standard light compaction test. Then we can write n into 6,000 because n into 600. So n into 6,000 total energy, and for how much volume? So 25,000 cc equivalent. So 593.01 energy required for the 1,000. So by equating this relation, we can get the n value is 24.71. So we have to write in the integer format. So we can write n is equal to 25. Are you getting my points? So these two things are just equated the Indian standard light compaction test, and compaction was going on in the embankment. So the energy is related with each other. So we can get the value of n is equal to 25. Here the question number 2. Compare the compactive energy used in the IS heavy compaction test with that of the IS light compaction test. So if we'll go through the IS code, we have all these data and we can calculate the energy important in case of the IS heavy compaction test. So we can get this value 275625 kg force meter per meter cube, or in the case of IS light compaction test we got this value 60450 kg force meter per meter cube. If we will take the ratio, we can get 4.56. So it means IS heavy compaction test usage 4.56 times the compactive energy that is used in the case of light compaction test. So the compaction curve. So the compaction curve, already I told you the compaction curve is the relation between the dry density and water content. So suppose we are performing a test in laboratory. So after doing the compacting process, so we can take the weight of the soil sample, and that is the W. So and weight of mold is given, so we can calculate the bulk density. And if we will take the sample, then we can calculate the water content. So by using the bulk density and water content, we can calculate the dry density, that is gamma D is equal to gamma T divided by 1 plus W. So if for all the tests, we have found that so many different tests, for all tests we have the dry density and water content, and if all these value plot in the graph, so we can get this graph, and that is called the compaction curve. And in this compaction curve, in this graph, so dry density we have put in the ordinate and water content put on the abscissa. So we can get this compaction curve. So if you see the curve, you can see that the first when increasing the water content, dry density is increasing. After at the certain water content, the dry density is maximum, and if you will increase the water content beyond that, then dry density is decreasing. Okay, so at the water content where the dry density is maximum, that is called optimum water content or optimum moisture content, right? So why it's happening, increasing or decreasing? So let's discuss all these things. So let's consider water content is less than optimum moisture content, and this phase is called the dry of optimum. And if you will talk about the water content is more than optimum moisture content, optimum water content, then that would be the weight of optimum. So let's discuss the dry of optimum, means water content is less than optimum moisture content. So what is happening in this case? In this case, soil is very stiff and it's a lot of wide spaces. So that's why the dry density is less. But if you will increase the water content, if you will add the water in this soil, so what is happening? Soil is getting lubricated and slip over each other, and they move into the densely packed position. So what we are getting the weight is we are getting W is getting more and the volume is getting less due to the closely packing. So that's why the dry density we are getting more, right? But if we'll see in the case of weight side of optimum means where the water content is more than optimum moisture content. So what is happening there? If you increase the water content, then volume of air will not change because that it is just at a maximum. It will not decrease further. So what is happening? If we are increasing the water content, so water particles are reduced and replace the solid particles of a soil. Or we know that density of solid particles is more than the density of water. So after the conclusion, what we can get dry density is decreasing when the water content increasing because the water molecule is replaced by the solid particles is replaced by the water. So we can get the less dry density. Okay. So theoretically we can calculate the maximum dry density. So we have the density formula. So where the S is the degree of saturation, W is the water content, G is the specific gravity of a solid particles, gamma W is the water content. In terms of air content, we can percentage of air we can calculate the dry density. So these two formula. So by using these two formula, we can calculate the dry density. For 100% saturation, what is the dry density? So put the S equal to 1, we can get this value, right? Or for the 0% air void, so if we will put the Na equal to 0, we can get this value. So by formula, we can see that these two formula is coming the same, means whatever we'll put the water content, so this two value will give the same value. Okay. So if we will draw a line, 100% saturation line or 0% air void line, it would be the same line. Means we can this line, whatever is showing the figure, we can say 100% degree of saturation line, or we can say the 0% air void line. Okay, because these two will give the same result, same dry density. Theoretically, maximum dry density that will give the same. But in the case of 80% saturation, so we can put the value of S equal to 0.8, we can get this value. Okay, or for the 20% air voids line, we can put the N equal to 0.2, so we can get this value. So by comparing this value, we can say that these two values are not equal. Means for a single water content, for a particular water content, the dry density will come different for the 100% saturation. So for 80% saturation line or for 20% saturation air void line. So this would be not same. We can say that the 100% saturation line is equal to the 0% air void line, or we can say that, or in the other way we can say that 80% saturation line are not equal to the 20% air void line. Are you getting my point? Okay. So here the next question number 3. The following results of the compaction test, and this data are given. Okay, and the volume of mold is given 1000 ml, mass of mold is given 1000 gram, and G is given 2.7. So we have to determine the compaction curve showing the OMC, optimum moisture content, and the gamma D, maximum dry density. Plot the 0% air void line. Okay, determine the S, where the S is the degree of saturation at the gamma D max. So first we have to calculate the gamma T, gamma D, water content, and the maximum dry density. So for the first test, we have the weight of soil. So we can calculate the weight of soil by reducing the weight of mold, where mold plus weight soil minus mass of mold. So mass of mold is 1000 grams. So by deducting we can get the 1925 gram. So that is the weight of soil. And we have volume. So volume of mold is 1000 ml. So we can calculate the gamma T, and we can also calculate the water content is showing the 10%. So we can calculate the gamma D value. So we got this value gamma T and gamma D in terms of gram per cc. And for gamma d of the soil corresponding to the 0% air content line, so we can calculate the gamma d. So we can use this formula where the W is the water content, and we can get the gamma d theoretical value. So 2.125 gram per cc. So this is the all result for the first test. So we can do the same procedure for the second test, same procedure for the third test. We can fill this table. So all tests we have the gamma T, gamma D, and gamma DS. So all this value, gamma D and water content, we can put in a graph. We can get this graph, and that graph is called the compaction curve. So we can by this graph. So gamma D value is 1.88. Okay. So gamma D maximum. So by formula we know that G gamma W 1 plus E. So by using this formula we can calculate the E. E is the wide ratio, and that we get 0.436. So we can calculate the S. So we have the formula ES is equal to GW. So we can calculate the S is equal to GW divided by E. So we have W. So what is the W? W is the optimum moisture content. And what we have? So optimum moisture content. So around 15 point something. So we can put this value G or E. So we can get the degree of saturation 88.55%. Factor affecting the compaction. So what are the factors which is affecting the compaction? And that is the water content. So you can see in this figure, already discussed in the previous slide. If you increase the water content, then first dry density will increase, and then it will attain some maximum value. And then if you increase the water content beyond that, then the maximum dry density will decrease. And what are the mechanisms behind in the wet side of optimum or in the dry side of optimum? Already have discussed in the previous slide. So this thing you can see in this figure also. Next one is the amount of compaction. So amount of compaction, or we can say the compacting effort. So if you increase the compacting effort, the maximum dry density will increase and the optimum moisture content will decrease. So in this figure there is a two compaction curve, A and B. A is the standard Proctor test and B is the modified Proctor test. And we already know that modified Proctor test has applying the maximum or more compacting effort compared to the standard Proctor test. So you can this graph you can see that the maximum dry density for the B compaction curve is more as compared to the A compaction curve, or in the case of A compaction curve, water content is more compared to the B. Okay, optimum moisture content is more compared to the B. So this thing you can see but this is not like that. If you will increase the compacting effort and maximum dry density will go on increasing. So what is happening if you increase the compacting effort? So the maximum dry density will get smaller, and finally a stage is reached beyond which there is no further increase in the dry density with the increase in the compacting effort. And the line of optimus, which is the join the peak of the compaction curve of a different compacting effort, follow a general trend, and this line more or less would be parallel to the 0% air void line. Next is the type of soil. So in this figure you can say that the variation of this graph is shown, compaction curve is shown for all types of soil, and dry density, water content is also shown and this line, a dotted line, is shown the 100% saturation line. So generally coarse grained soil can be compacted to a higher dry density than fine grained soil. And for a well graded sand attains a much higher dry density than a poorly graded soil, because a well graded soil means a soil has all size of proportion there. So in case of the cohesive soil or in case of a clay has a high air voids, and the soil attains a relatively lower maximum dry density, and these things you can see in the figure also, compared to with the cohesionless soil. And such soil require more water than cohesionless soil than sand, and therefore this soil has a maximum moisture content, maximum optimum moisture content. The next one is the method of compaction. So maximum dry density depends upon the water content, amount of compaction, type of soil, but it's also depend upon the method of compaction, how we are compacting, what method we are adopting to do compaction. So for the same amount of compacting effort, the dry density will depend upon the whether the method of compaction utilizing the kneading action, dynamic action, or static action. So these things depends upon the what method we are adopting. Next one is the admixture. So we can increase the compaction property by using the some admixture like lime, cement, and bitumen. And for a different method of compaction gives their own compaction curve. And for different method of compaction, their effect of compaction on the properties of soil. So the first one is the soil structure. So on the dry side optimum, it means water content is less than the optimum moisture content is a flow chloride structure, or on the weight of optimum means water content is more than the optimum moisture content. Soil structure is dispersal structure. So in this figure you can see this. So at a point A and point C has the same dry density but different water content. So at the point A where the water content is low, so the attractive forces are more predominant as compared to the repulsive forces. But when you will increase the water content, or in case of C where the water content is more, so the repulsive forces are more predominant as compared to the attractive forces, so that the structure will come dispersal structure. But if we will compare the same water content, if we will compare the different compacting effort, so you can see this point A and point E has the same water content but dry density is different, because point E at a point E the fluctuated structure is more oriented due to the higher compacting effort compared to the point A. Second is the compressibility at lower stress. The weight side of optimum is compressibility is more, because the strong bond between the interparticle bond in a fluctuated structure do not allow the particle to be displaced. But in the case of high stress, dry side of optimum, its compressibility is more in the dry side of optimum, because once the this strong bond is broken due to the high stress, they allow more displacement, more compression because of the larger volume of voids. Stress-strain relationship. So in this figure you can see this in the dry side of optimum. So there is a graph showing the higher stress resistance, or in the case of wet side it is showing the strain curve is flatter. So because of in the dry side optimum the structure is a flocculated structure, and this flocculated structure has a strong bond. So due to that strong bond, this showing the higher stress resistance. But if this structure this bond has broken, then it will fall down. So in this figure you can see that dry compacted, it is go on increasing, it's give the peak value and then is falling down. But in the case of wet side optimum, the strain curve is flatter and there is no peak of this curve, and this shear strain resistance or stress resistance is minimum in the case of wet side optimum. Shear strength undrained and after saturation. So here the same mechanism you can see in this figure. In the case of dry side optimum is high, or in the case of wet side optimum is less, because of the bond showing the more resistance to the more showing more resistance, and then that's why the shear strength is more high. Or in the case of wet side optimum, the straination curve is flatter and is showing the less shear resistance. Permeability. So you know that permeability depends upon the size of voids, and in the case of flocculated structure, if we increase the water content in the flocculated structure, then it's go on packing, is change the orientation, and the volume of voids get reduced, size of voids get reduced, and due to the size of void reduction, the permeability is decreased. But in the case of wet side optimum, slightly increase, because in the wet side optimum water content is more and showing the permeability and flow of water. Swelling. So swelling is more in the case of dry side optimum because the water deficiency is more in the dry side optimum. Pore water pressure is less in the dry side optimum because the water content is less. Shrinkage. Shrinkage in the dry side optimum is less, and in the wet of side optimum is more, because in the wet of side optimum that soil structure is dispersal structure, and this structure is closely packing. So this compression is more and closely packing. So this showing the on drying this volume changes is more. So this wet side optimum is shrinkage is more. Control of field compaction. So whatever the dry density we are getting in the field, we can compare from the standard Proctor test or from the modified Proctor test. So basically the ratio of the dry density in the field to the maximum dry density is known as the relative compaction or percentage compaction. So we can write this formula. So field control test may be destructive or non-destructive. So compaction control by measuring the dry density and water content. So dry density we can measure by core cutter method, or by we can method sand replacement method. So these two methods are commonly used in the field, but on the non-destructive side we can use the nuclear method to calculate the dry density. So to calculate the water content, so we can calculate water content by oven dry method. But oven dry method is sometimes not feasible because it takes a lot of time. It's like 24 hours to get the water content. So instead of oven dry method, we can use the sand bath method, alcohol method, or calcium carbide method. Or sometime we can also use the for the field purpose we can use the Proctor needle method, or it's also known as plastic needle. So the Proctor needle consists of a rod attached a spring-loaded plunger, and the stem of the plunger is marked to read the resistance in Newton. Okay, and the needle sunk has a, you can this figure, but in figure it's not showing clearly, but you can understand the things, and that needle sunk has a scaling. Scaling is there. In terms of scaling, there is a measuring it there. You can measure the penetration, you can measure the depth of penetration by reading that scale. So that equipment provided a series of needle with different cross section 0.25, 0.5, 1.0 and 2.5 centimeter square. So for different soil we can use the different cross section of needle. So we know the different area of cross section, and we can know the resistance force. So by force divided by area, we can calculate the penetration resistance in terms of stress or in terms of kilonewton per meter square, right? So after measuring the penetration resistance, so we can calculate the water content by using this calibration chart. So we can use the water content by using the Proctor needle method. These are some reference that we have taken. So first is what this video, and whatever the question I have solved, thus try to solve some gate problems on ES problem, and I will give you more questions, so that and after some time I can give the solution also. So please update the feedbacks. We'll give the feedback, and that I will consider that all these things that attendance and it is compulsory for everyone. Okay, thank you.